Welcome back to Mr. Vaughn's classroom, where math is made easy. Before we get started on today's video, I'd like to ask you to please help support the channel by hitting the subscribe button and giving this video a thumbs up. Today we're looking at Unit 1, Constructions and Rigid Transformations. This will be Lesson 16, and we're looking at more symmetry. The learning goal in this lesson is to describe more symmetries of shapes. If you remember in Lesson 15, we talked about symmetry when it came to reflections. We were looking for a line of symmetry where if we reflected over that line of symmetry, the shapes would lay right on top of each other. Today, we're going to be looking more at lines of symmetry or points of symmetry that we can rotate around and then create symmetry. So we again have one learning target for this lesson. Once we get done with the practice problems, we'll come back and review this learning target just to make sure you understand everything you need to. And the one learning target today is that you can describe the rotations that take a figure onto itself. So you can describe, am I rotating clockwise or counterclockwise, if that matters, or I'm rotating 180 degrees, I'm rotating 120 degrees, whatever the description is that you need to give in order for somebody else to understand how you're rotating in order to create that symmetry. For the glossary terms, a lot of these we've seen before. We'll start out with assertion. This is a statement that you think is true, but you have not yet proven that it's true. Congruent is when you have figures that wind up with the same side length and the same angles, and that happens because you do rigid transformations where you either translate the shape up, down, left, or right, you rotate the shape clockwise or counterclockwise, or you reflect the shape over a line of symmetry, and therefore you end up creating a shape that you've not made any bigger or any smaller, and you've not changed the angles, which means you've created a congruent shape. Directed line segment is kind of a combination of lines and line segments. Lines go on forever in both directions. Line segments have endpoints. A directed line segment shows you which direction the line segment is going. So in this image on the right, not only do we have line segment AB, but we know this line segment is specifically going from point A to point B because of that arrow we added near point B. The next term is image. When you do a transformation, your original shape is the original, and the one that you create is now the image. So here on the right, we have triangle ABC. That's the original. It is translated up and to the right, creating triangle A prime, B prime, C prime, and that one is the image. Next, we have line of symmetry. We talked about this in lesson 15. This is simply a line where if we were to reflect across that line, then the lines would be directly on top of each other. So in the first hexagon, we could fold it in half vertically and the two sides would match up. In the middle, we could fold it in half diagonally and the two sides would line up. And for the eye shape on the right, we could fold it in half vertically and the two sides would line up, or we could fold it in half horizontally and again the two sides would match up. Next we have reflection. Reflection means you have a line of reflection, in this case line M, and by reflecting over that line of reflection, you would create the object on the other side in the same position. So in this case, we have point A. Line M is the line of reflection, which is also its perpendicular bisector. So therefore, if we reflect A across line M, we end up creating A prime. Reflection symmetry simply means that a figure has reflection symmetry if there is some type of reflection that you can do that takes your shape onto itself. So in this case, instead of reflecting the entire X over a line of symmetry and creating a congruent X shape, we're going to fold half of the X over on itself, and we can do that vertically and horizontally. Rigid transformation, these are translations, moving up, down, left, right. These are rotations, clockwise or counterclockwise. And these are reflections, where we have a line of reflection and we reflect the shape across that line. And what happens is we end up creating a congruent image that has the same side lengths and the same angles, because we've not made it any bigger or any smaller, we've simply moved it. So A translates to B, B rotates to C, and C reflects to D. Rotation has a center and a directed angle. So on the left at the bottom, we would say that P is rotated counterclockwise around O for the amount of T degrees, and it creates the image of P prime. And then on the right, we would say that the quadrilateral ABCD is rotated counterclockwise 120 degrees, and it creates the image A prime, B prime, C prime, D. D is the center point. The other 3 points rotate around it, so D remains the same. The new glossary term we have here is rotation symmetry. A figure has rotation symmetry if there is a rotation that takes the figure onto itself. We don't count rotations using angles such as 0 degrees and 360 degrees that leave every point on the figure where it was. So down at the bottom, we have a sample of a hexagon. So we would not consider 0 degrees because we would be leaving the hexagon where it is. We also would not count 360 degrees or any multiple of 360 degrees because you would rotate the entire hexagon one full circle and every point would be exactly where it started. But what we would count would be something like this shaded 60-degree rotation. There's 360 degrees in a circle. A hexagon has 6 sides. So 360 degrees divided by 6 means that if we rotate 60 degrees, this top right point would rotate to the top left point, so it's not in the same place, but we would still end up with a hexagon that looks exactly the same. So the points move, but the shape itself stays exactly the same. So we could rotate it 60 degrees, we could rotate it 120, 180, 240, or 300. We just wouldn't count the 360 because then every point would be right back in the same spot. Our next term is symmetry. We say that a figure has symmetry if there is a rigid transformation which takes it onto itself, not counting a transformation that leaves every point where it is. So again, we would not say that we would rotate it 360 degrees because then every single point stays right where it is. But if we can do a translation or a rotation or a reflection where we create some type of symmetry and the points are not all in the same spot, then that is what we would consider symmetry. Next, we have theorem. This is where we've taken that next step from an assertion. So an assertion was simply the statement. The theorem is once we have proven that statement to be mathematically true. And we have translation. A translation is defined using a directed line segment. It takes a point to another point so that the directed line segment from the original point to the image is parallel to the given line segment and has the same length and direction. So here we have line segment T. We can have point A down at the bottom, translate it up and to the right in the same direction as line segment T to create A prime. Now we've shown that we have done a translation from A to A prime. Now that we've gone through the introduction, if you do have any questions, go ahead and leave them in the comment section. But let's go ahead and get started on the practice problems. So now we can start on the practice problems for lesson 16. In practice problem number 1, for each figure, identify any angles of rotation that create symmetry. So remember that this time we're looking for angles of rotation as opposed to a line of symmetry. So we want to know, can we turn these shapes and create symmetrical or congruent shapes? So the first one is a little tricky because we have two repeating shapes. We have shape 1 and shape 2, but they're different colors. So we could answer this in two ways. If we count color, then rotating this would put the black where the white is and the white where the black is. And if we're counting colors, then that's not symmetrical. So we would say if we count color, no angles of rotation. Cause symmetry. That would be the first way to look at it. But if we did not count colors, then the way that I would look at this is that I have two repeating shapes. I know that a circle has 360 degrees. So I would take 360 degrees, I would divide that by the two shapes, and I would get 180 degrees. If I rotate this symbol 180 degrees, either clockwise or counterclockwise, it doesn't matter, then not counting colors, the curve shape, the black one would go where the white one was, and the white one would go where the black one was, and the white and black dots would switch places. But since we're not counting color, this would be symmetrical. So if we don't count color, 180 degrees of rotation creates symmetry. So that's how I would answer the first one. Let's look at number 2. Here we have a rectangle. Now the colors won't matter this time. And if I were to rotate this triangle all the way around, it would be 360 degrees. Now again, I have two distinct shapes here. I have these thicker triangles on the left and the right, and I have these thinner triangles on the top and bottom. So since I have two unique shapes, if I divide it by 2, then again that equals 180 degrees. So if I were to rotate this rectangle 180 degrees, the triangle I labeled A on the left would rotate around to where the triangle labeled A is on the right. The one on the right would rotate around to where the one on the left is. The triangle labeled B on the top would rotate to the bottom, and the triangle labeled B on the bottom would rotate to the top. So 180 degrees of rotation will create symmetry. And then the third shape here, we have 3 legs that are all the same. We've got leg 1, leg 2, and leg 3. So I would take my 360 degrees, I would divide that by 3, and that gives me 120 degrees. So if I were to rotate 120 degrees, leg 1 would go to leg 2, leg 2 would go to leg 3, and leg 3 would go to leg 1. And I would have the same image. But then, this is now 1, this is now 2, and this is now 3. But I could rotate a second time, 120 degrees, and the same thing would happen. So I could do rotations of 120 degrees and 240 degrees of rotation will create symmetry. Because now leg 1 goes to where leg 3 is, leg 2 comes around to where leg 1 is, and leg 3 comes around to where leg 2 is. So both of these angles of rotation will create symmetry. It doesn't matter whether it's clockwise or counterclockwise. It'll work in both directions. I hope this helps you understand angles of rotation, creating symmetry. But if you do still have any questions, please feel free to leave a comment below. Now let's go and take a look at practice problem number 2. Practice problem number 2. A triangle has rotation symmetry that can take it to any of its vertices, to any of its other vertices. Select all conclusions we can reach from this. So, again, we're looking for rotational symmetry. And we're going to have a triangle. And we want to take any vertice to any other vertice. So, think about what type of triangle this needs to be. If I tried an acute triangle, my sides are not the same and my angles are not the same. So if I tried to rotate this, I'm not going to end up with every corner ending up exactly where another corner was. Same thing if I tried an obtuse triangle. If I try to rotate this, again, I'm not going to end up with every corner going to another corner. So that means I'm going to need an equilateral triangle. If I have an equilateral triangle, then I can rotate each of these corners to the next one. So that means we need to have an equilateral triangle. Now, with that in mind, let's look at our options. Choice A says all sides of the triangle have the same length. And that is true with an equilateral triangle. So A is going to be correct. Statement B, all angles of the triangle have the same measure. And with an equilateral triangle, That is also true. Option C, all rotations take 1/2 of the triangle to the other half of the triangle. Well, if I cut this triangle in half, and we kind of color one side green here, and we color the other side blue, then when we rotate this, remember it says all rotations. Well, if I rotate this to look like this, even if I've taken it to another corner, well, this line of symmetry, I'm going to rotate with it. So now my line of symmetry goes through here. This would now be my blue half. And this would now be my green half. And we did not take the green half to the blue half. And we did not take the blue half to the green half. So C would not be a true statement. So on this one, the first thing we needed to figure out is that we could not do this with an acute triangle. We could not do this with an obtuse triangle. We would need to have an equilateral triangle. Once we knew that we needed to have an equilateral triangle, then by definition, that means all the sides are going to be the same and all the angles are going to be the same. However, part C is wrong because not every single rotation is going to take 1/2 to the other half. In fact, it won't do it unless we rotate a full 360 degrees. I hope this explanation helps you understand this problem. If you do have any questions, please leave a comment below. Now let's go ahead and take a look at practice problem number 3. Practice problem number 3 is going to be the last problem for this lesson. Once we're done with it, we'll go back and we'll review the learning target. Select all the angles of rotation that produce symmetry for this flower. So with this flower, we have 4 distinct petals. We have this petal in the upper left. We have this petal in the lower left. We have a third petal in the lower right. And we have our fourth petal in the upper right. So if we are going to have angles of rotation that produce symmetry, then we're going to need to take 1 petal to each of the other 3 petals. So to rotate a full time around, that is going to be 360 degrees. And since we have 4 distinct placements for the petals, that means every 90 degrees, we're going to be able to put one petal where the next one is. So the first rotation, I'm going to concentrate on this blue petal. If we rotate 90 degrees, then the blue petal would now be where the green petal is. So that means B is a correct answer. The next rotation we could do is if we rotated from the blue petal all the way around to the yellow petal. So that's the 90 degrees to get it to the green petal, and then another 90 degrees to get it to the yellow petal. So that's a total of 180 degrees. So D is also a correct answer. And then the final rotation we could do is to go from the blue petal all the way down and around up to where the pink petal is. So that would be the 90 degrees to get it to the green, 180 degrees to get it to the yellow, and 270 degrees to get it all the way around to where the pink petal is. So F would also be a correct answer. And remember, we're not going to count 360 degrees because that just puts everything back right where it was. So that means B, D, and F are the correct choices, and A, C, and E are incorrect. Hopefully, this little diagram and explanation helps you understand this problem better. If you do still have any questions, feel free to leave a comment below. Now let's go and take a look at that learning target just to double check you understand everything you need to from this lesson before moving on to future lessons. All right, let's review the learning target for lesson 16. On this one, it said that you can describe the rotations that take a figure onto itself. So if you think back to the problems that we did, what this is talking about is how do we rotate? Do we do it clockwise, counterclockwise? How many degrees do we do it? Where we can take something like that flower in the last problem, and if we rotated it 90 degrees in either direction, we could rotate it so that the 4 petals wound up exactly where the other petals were. And therefore, we have a rotation that brings that image of a flower onto itself without putting it right back in the exact same spot. So we didn't rotate it a full 360 to put each colored petal where they started, but we rotated 90 degrees to take the blue to the green. We rotated 180 degrees to take the blue to the yellow. We rotated 270 degrees to take the blue to the pink. And that also then moves the green to the yellow, and the green to the pink, and the green to the blue, and so on. So that's what we were looking at in this lesson, is that we say that there is rotational symmetry if we're able to rotate something other than 0 degrees or a multiple of 360 degrees so that we end up with the same image, but the points didn't wind up in the exact same spot. So the flower turning a triangle an equilateral triangle, 120 degrees makes it look like it's the same, but takes one vertice to another. Taking a square and rotating it 90 degrees around the center. It'll still look like the same square, but the points won't be in the exact same spot. So that's what you need to be able to take away from this lesson. So if you do understand that, you're exactly where you need to be moving into further lessons. If you do still have further questions, please feel free to leave a comment below. If you found this video helpful, I would ask that you give it a thumbs up. In the bottom left, you should see another video of mine that YouTube is recommending for you. In the bottom right corner, you should see the subscription button for the channel. It really helps me out if you subscribe to the channel. And please feel free to engage with a comment below. I look forward to seeing you in the next lesson.